My name is Garth Henson, as was mentioned. I do work at the Walt Disney Company. I've been with the company about 5 years now. Thank you. That's how I feel still, every day. I worked out of the Seattle office for about 4 years. I work with corporate technology there. What we do is basically platform tooling, anything we need to build to enable the different brands to do what they need to do. So right now I'm working with ESPN, we work with ABC News, we work with Parks and Resorts, we work with all the different brands from an infrastructure, architecture, application, basically whatever we need to build. Right now, it's kind of fun because most of what I build is Node on the back end, and we do full stack all the way up to, we do React on the front end. And so most of the stuff we're working is JavaScript end to end. One of the reasons I am excited about this talk is this is something that is an ongoing project, is we're trying to figure out which applications we should move to not only into the cloud, but into a serverless architecture. The nice thing is that in most cases, we can keep running JavaScript end to end with maybe a little bit of bash in there for some of our Docker containers and entry points and that type of thing. So that's what we're going to talk about today. Serverless is one of those very interesting terms. It's been a buzzword for a long time, and it's one that I really don't like, honestly. Serverless sounds like we just don't have servers anymore, which, of course, we know they just are going to go away and everything runs on magic, right? At least at Disney, that's how it works. But what is serverless? Serverless computing, based on a Wikipedia definition here, it's really a cloud computing execution model. It's a process, it's a way of thinking in which the cloud provider dynamically manages allocation of machine resources, and then the pricing itself is generally based on the actual consumption of the processing. So whatever you use is what you pay for. So obviously that means, I'm not there yet, sorry, I'm jumping ahead. So this diagram kind of breaks down into a couple different categories, all of the things we would talk about as a cloud offering. And so most of these, I hope, many people in here are familiar with some of the different broad categories. IaaS is pretty common. You're going to have infrastructure as a service, whether that's an on-prem data center that you're having to pull resources from and allocate, or you're using EC2 instances, or you're using compute instances from whatever provider, cloud provider you use. You basically have to provision what you need, and you have to assemble all of your pieces before you can deploy the code to it, right? We're familiar with that. And then you've got the SaaS offerings, which I think most of us are also familiar with, where I just don't either want to take the time or the money to build it. I'd rather put the money into paying for the service and just use it where it stands and let them manage the SLAs, let them manage everything else and the support layers. We just don't want to take that on ourselves, so we're going to buy the service from somebody else, use it in place, and continue processing. And then more recently, we're getting more and more capabilities of moving things into the cloud on top of your PaaS offering. So you've got your platform as a service that you're going to start leveraging. And what's really interesting, and we'll talk a little bit more about this, is with things like Direct Connect for AWS, and there's other things with some of the other service offerings as well, you can actually start running some of these platform offerings on your own private networks. And so even though it's still managed completely remotely by your service provider, you can actually run it on your private network as well. So you're starting to get the best of both worlds, where you can start leveraging these other pieces, but yet keep your connectivity the way it needs to be for your broader application. And then on this diagram as well, you'll notice that towards the top here, we have the functions and the database as a service, some of your things like your NoSQLs, Firebase, or you've got your Dynamodb type of thing. Those are typically what we group into what we would really call serverless. Those are the things that basically everybody says, oh yeah, just use it. It'll scale, and you just pay for what you use, which is true, but we need to make sure we understand what that actually means. So this is, if we're in a smaller room, I would pause for questions, but I will say now, if you have questions, please do come talk to me afterwards. I don't have all the answers. I'm still learning a lot of this, but I do want to share what we've figured out so far. So, of course, once we understand all of these, this brings us to the conclusion I've heard so many times: no more servers, yay, everything's awesome, we don't have to worry about anything anymore. No, actually, all it means is it's not my servers. the problem or the hiccups, the things we have to be aware of don't go away. They just move to another location. The concerns we have to be aware of just change. They don't go away. Why do we care? Why does it matter? Well, if we look at the benefits of serverless, there's several, and then there's other things we have to be aware of as we move into this architecture. First of all, cost. Cost really is almost unanimously cited as the driving reason to move to serverless adoption. Everybody's like, oh, it's just cheaper. Everything should be serverless. Everything's cheaper, which can be. On-demand execution, built-in elasticity, optimizes utilization, uptime, reliability, everything's higher. This is all true. This is great. It's fantastic. But I want to see there's a specific word right there. The savings can be insane. If they're built correctly for the appropriate applications, they are incredibly cheaper to run. However, there's that key word of if we build them properly and we use it for the appropriate application, it's cheaper. So keep that in mind. Scalability, by definition, we're using serverless offerings. We're using hosted and managed solutions. And so scalability is built into it. Reliability, it's really based off your provider's SLA. So we have all of these great potential benefits that we can get out of moving applications into a serverless architecture. But we need to be aware, I love this quote, the most common currency to pay for benefits in our application architecture is complexity. So how do we get, I don't know if, I don't have the diagram up here, but you've got different pivots that you can actually pull on in any application, right? Any architecture. Management comes down and says, hey, this has to run less expensively. Okay, great, it's going to be slower now, or it's going to be, there's only certain things we can pull on. And in order to reduce the cost and increase the performance and the scalability and reliability, the easiest way to do that is to increase complexity. Now, what does that look like, though? Well, in this diagram, we kind of see the stepping stones between moving from our old monolithic applications into a standard, what we would call the microservice infrastructure or ecosystem. And basically what happens is from step 1 to step 2, all we've done is we've broken all of those bits of logic, all of those sections of the code that were running all in one big application. We've broken them out into their own smaller services, which is great, but now we have all this wiring in between. So we've introduced some complexity of the wiring, breaking a monolith into microservices. Now, did we gain performance, reliability? Yeah, if it's done right, absolutely. But we've added some type of complexity. So when we're moving from microservice infrastructure or architecture into a full serverless stack, we're introducing far more wiring in between all of the pieces. So the complexity is potentially much greater for the overall application, even if the individual pieces of code that we as engineers are managing are much, much simpler to maintain. So the overall application architecture we've got to be aware of as we go. And then all of this, of course, is built on top of some type of a platform that we're paying for or we've spun up internally. So moving on here. Here are some of the things that we have to be aware of. As the heading up here says, serverless is cheaper, not necessarily simpler. Anybody played with S3 much and had any issues with eventual consistency? A couple hands, awesome. Okay, so if you're not aware of what eventual consistency is, S3, and I told Miles I was going to have to apologize to him. I don't know if he's in here. All of my examples are AWS. I am intentionally doing pretty generic examples because these are things you can do on any service provider. I'm not doing a sales pitch for AWS. I just what I know the best. But eventual consistency basically means you can drop an object into an S3 bucket for storage, and it may or may not be available for a read right away because it has to replicate across different data centers, it's got to replicate across regions, and when your GET request or your pull request goes back out, if it hasn't replicated all the way across, you might hit a bucket or a region where it hasn't propagated yet, and so even though you just wrote it and you got a success, it may not be available to read yet. And so we actually had a couple projects where we're like, oh, serverless, awesome. We're going to do one Lambda here, and it's going to drop something into S3, and then it's going to fire this thing off over here, and then the other Lambda is going to pick it up and do more processing with it, and it wasn't there. And the entire flow grinds to a halt, and we realized that, oh, we need to call the AWS guys. So we get Amazon on the phone, we're talking with them, and the question, of course, well, did you read the SLA? No, I didn't. And S3 is eventual consistency. There is a window of time in which they are still within their SLA, and as long as you can read it back out within a certain length of time, they're okay. And so these are things like the fault tolerance, asynchronicity, as you're doing multiple Lambdas that are stateless. You've got things like this that you have to start juggling, where you can do it at an application level in a monolith or even in microservices where each microservice could maintain some type of state. You now are introducing logical chunks that are stateless that have to be aware or be able to retrieve or rebuild or saturate or do something to be able to continue processing. And so things that before were somewhat intuitive within the application architecture are now becoming things we have to manually think through and deal with, or at least be aware of. Latency, the only reason I bring it up here, every new network hop can introduce latency. So if you have something, let's say we've got 3 microservices, and they're talking nicely together, and every new request hits all 3 of them, and it's a handoff. You've got the inbound request, and then you've got at least 2 hops. So you've got 3, but if we break that out and it turns into 6 different Lambdas or whatever, you're doubling the number of network connections and the network hops you're having to make to process something. So you've got to be aware of the increased latency potentially. Okay, and again, these are all just be aware of them. I'm not saying don't do it, I'm just saying be aware of what the potential gotchas are. Let's see, fault tolerance. What happens if an asynchronous Lambda spins up and fails and it can't process? And it's responding to something that it pulled off of a queue? Have you thought through what's your dead letter queue look like? Are you going to actually do some retry logic? What is your fault tolerance for it? What's your retry? All of these things we have to start thinking through on a higher level or broader scale. APIs, messaging schemas, how are you going to have all of the different pieces talk to each other if they're on the same process? All of these different things. Rolling upgrades, how do you manage your actual upgrades of the individual Lambdas or whatever piece you're upgrading? Are you changing the signature of the payload you're dropping? What are all of the different pieces like that? Let's see, and there's more. So I've heard from a lot of people that, hey, just do everything serverless. It's a solve-all, it'll cure everything, and it's really not. If you approach it as a cure-all, if you approach it as a silver bullet that's going to fix all of our problems, I'm afraid people are going to be very disappointed. Now, again, I say all of this, and I'm a very big proponent of using serverless, so don't get me wrong. It is a fantastic tool, but as with any other tool, you've got to use the right tool for the right job. And so every application, if you're considering serverless as a potential architecture, you need to evaluate your actual system, what it is you're trying to build, and what the benefits are. What is your ROI? What's the cost going to be? How many requests are you going to have? And we'll look at a couple examples here in a minute where we can actually talk through some of those concerns. So let's build a little bit. This slide, we're going to talk through a couple of the options in the AWS toolset that actually we use regularly for serverless applications, so broader architectures. Some of these are arguable. They fall into slightly different categories. Maybe somebody will be like, well, that's not pure serverless. That's DBAS or something. Yeah, I get that. But overall, from a serverless architecture standpoint, here's a few things to be aware of. We use Route 53 anytime we can to do DNS resolution because it ties so seamlessly into some of the other pieces like the API gateway. If you have not looked into the API management structures for several of the different cloud providers, API gateway is great. The way you can define and manage configuration for even authentication and header parsing, different things like that is pretty slick. Lambdas themselves, this is pretty standard. This is what every provider has as their cloud functions. You provide enough logic to run as a single logical execution. And you want to break it down and make sure you don't throw too much in there. You're going to run within restrictions in the different providers. such as within Lambdas, if you're running more than, I believe it's a 5 meg payload in a post request in or into the context into the Lambda is your cap. It also has a time limit of a 5-minute processing time. So anything beyond that, and it will automatically shut it down. So there are things like that you just have to be aware of, which will help you discern where in your logic to slice up the pieces to make it affordable and still be able to process. So Lambdas, let's see what's next. S3, this is your object stores. This is basically, AWS makes it very distinct that it is not a static asset store. It is an object store. You basically drop anything you want in there. This is the one that has given us trouble with eventual consistency. You just have to be aware of that. And then we'll look at Dynamodb. This is our new NoSQL store, highly scalable, incredibly fast connection speeds, read speeds, write speeds. And then SQS. And the reason I threw these up on here is because these are the ones we'll actually talk through on a couple of the architectural diagrams that we'll look at in a moment. So SQS is just what it sounds like. It's a queuing service. It's a hosted and managed queuing service. You set it up, and you start dropping items into it, and then you can reach out to it and check to see if there's anything on the queue for you to resolve. And it supports both standard queuing as well as FIFO queuing. So you can do a lot of different things with it. So one of the examples I want to talk through is a problem space I ran into where we had a couple APIs internally. These were APIs that had been spun up, and as we all know, there's no such thing as a proof of concept that stays a proof of concept. Anytime you show it to somebody, somebody starts using it, and now you have to support it. And we had several APIs that had been built internally for different teams, and a security audit came through and realized that we had multiple APIs that had access to data that were not fronted with any type of authentication. Now, good news is they were only on the internal network. However, they still were not fronted with authentication. So we were tasked with figuring out a way to try and front existing APIs with basically an OAuth-style authentication of some sort, where we could give API keys out to only those who need access to it, and we could do some type of token exchange to grant access into those APIs. So if you've ever done something like that before, where you've had an existing API and you've had to try and put something in front of it, it can be extremely challenging. In this case, we came up with something that worked decently well. Let's see if I can point over here. Essentially, the goal is we have an application layer down here. So this is something that was already existing. Okay, the application's there, the API is being hit, but there's no security layer in front of it. And so what we were able to do is take a, right here, the API gateway, and set up basically just an authorization password exchange. So you can take your API key and your secret, and you can hit an endpoint here that will reach out into this is kind of where the application layer, I guess, from the OAuth thing that we created. And there's a Lambda here that's your authenticator that really just checks your password. If you're in the API keys that have been granted, it checks to make sure you've got the appropriate role. It creates a new token. It drops the token into another DB table, another Dynamo table. The reason we chose this architecture is DynamoDB tables allow you to specify a TTL on every item that you drop into the table. And at that TTL, it will auto-expire that item and remove it from your table. So for this solution, it worked really well because if we had, let's say we had 5-minute tokens and we only wanted them good for a certain amount of time, we could drop them into our token table and they would auto-expire in that amount of time. We didn't have to do any manual cleanup, which was fantastic in this case. Once that's done, the authenticator simply returns with the token that they just generated, and the user or application, whatever it is that's hitting the endpoint, then can pick up that token, pass it off to the API that they were trying to reach anyway, and provide an authorization header with a bearer token on it that then fires off a secondary Lambda that all it knows how to do is authorize. The only thing this Lambda does is it takes the header and it looks in here to see if it exists and if it has the appropriate scopes for you to execute what you're trying to execute. And API Gateway right here actually has a concept of Authorizer And the authorizer basically says you can check your token, you can build up an AWS, what's the term? Lost my train of thought. But you basically build up your policy, that's what it is, that grants or denies access to what they're wanting. And the API gateway will receive that policy and actually cache it at that layer. So all subsequent requests to that endpoint will actually use the same policy that's been cached. So you can actually replay tokens without having to overload the number of executions of your Lambdas, which ends up saving even more money. So I got to jump ahead. I just got the signal here. So application layer, you end up doing the handoff once everything's been granted and you move forward. This one, I think, is a little more approachable. This is a full-on, if we wanted to do something like a mailing list, we could actually have the Route 53 layer, the DNS resolution, hit an API gateway. We can have the gateway simply drop payloads into like a registration bucket. So a Lambda can fire off and be like, oh, great, you wanted to register. We're going to drop your email address into a DynamoDB table. And then you might have an administrator come in later and want to actually send an email, and they can hit a different endpoint on the API gateway, and it'll kick you over and build up a queue of all the emails that need to be sent, and then you can process them however you like. Now, I want to jump real quick and see if I can do a quick demo or not. So give me one moment. I've got just a couple minutes here. And all right, so this is a whirlwind. I will tell you now, I'm going to probably have to cut this very short. So if you have questions or you want to walk through this with me later, please find me. I'm happy to talk through as much of this as I can. API Gateway essentially allows you to just specify all of your endpoints like you would. It's almost, if you've used Swagger or anything like that, or you use Happy.js or anything that where you can do a declarative style APIs or routes, that's basically what we can do here. And then you wire it up directly to a Lambda. So you've got up here, you see the type is a Lambda proxy on the integration request. Basically what that tells the API gateway to do is to do a little bit of pre-processing and create a context that's going to hand off to your Lambda function. And so then you write a little bit of node in your Lambdas over here. Come on. Slow Wi-Fi. Where are we at? There we go. Oh, come on. If that loads, that's great. But there's some node. It's just a function that accepts a context and some additional parameters depending on the type of Lambda you want. There's a lot more complexity. I'm smoothing a little bit of it over. But it gets handed a context. From that context, you can basically look at the payload that was parsed out. You can look at the headers. You can make all kinds of different decisions within your Lambda of what to do further. And so in this case, I'm trying to load the email sending one. In this case, we would actually grab from DynamoDB our entire list of emails that have been registered. We would then take the body that was sent to us, and we would just kind of line them up together and send off an email to each one of the users. So it's a really, really rudimentary email management or marketing type thing, but that's essentially all that there is in it, is the ability to wire up your API directly into a Lambda that knows how to process, glean the data that's been dropped in from somewhere else. So that never did load, did it? Nope. All right, well, come to me later. We'll run through it. So again, that's all this diagram is showing. In this case, what I was doing is dropping it into a queue in SQS, and then we'd be able to pull that queue and pull out the generated emails to send off. You could have an iron port or something like that to actually process major email loads. So besides that, a little bit of homework. There are multiple things to consider we have not talked about. This is a very high level. We have things like IAM roles, you've got security models, you've got VPC for your private cloud, you have Direct Connect, which I did mention, which lets you run things on your internal or business network so that you can actually control your security a little bit better or have security shared between internal and cloud applications. If you're using MySQL, Postgres, something like that, there are offerings to let you do that with your database and let them scale it or host it for you. And again, by them, pretty much all the providers have this type of thing. You've got caching layers. You've got all kinds of different things you can use to accent or complement the serverless offerings we've looked at to build out a much broader and more secure application. So I just did the demo, and so that's it. Thank you very much.